Welcome back, my friends. In this, we will continue our discussion of confidence intervals, and we're going to examine the purpose of the central limit theorem in this particular video. In the central limit theorem, we want to review some things that we've discovered about normal distributions of raw data. For instance, we can establish confidence intervals to trap required portions of data between z-score boundaries. And if you'll notice here, this is the standard normal curve. We have a mean of 0, standard deviations of 1. And between these boundaries, we can trap certain portions of raw data. For example, the confidence interval to capture 95% of the data is represented here. Between negative 1.96 and 1.96 standard deviations, one below the mean, one above the mean, we can capture 95% of the data. If we want to capture 90%, we would be 1.645 standard deviations above and below the data. If we wanted to capture only 70%, it's 1.04 and negative 1.04. The thing that you need to see here in these is that as you become more confident, the interval widens. As you become less confident, the interval narrows. And also I need you to see that these z-scores capture a specific portion of the data. 95% will always be captured by 1.96 standard deviations above and below the mean. 90% always by 1.645 above and below the mean. 70%, 1.04 above and below the mean. These z-scores don't change as you look at specific amounts of data. 95%, 90%, 70% all have a standard z-score that you work with. Now, there's some observations with this. In this type explanation, the mean and the standard deviation are known. And the confidence intervals are to describe relationships when the mean and the standard deviation are known. In other words, we know the population mean, we know the population standard deviation, and we're using confidence intervals to describe those relationships. Let's draw some pictures of these phenomena. In this particular picture, we have the population, and given the mean and the standard deviation, we can establish a confidence interval. If we take a sample of the population, given x bar and s, we can establish a confidence interval. But in this case, we know the population mean and we know the population standard deviation. How likely do you think we really are to know the population mean and standard deviation? Well, let me answer that for you. We're really not very likely to know the true mean and population standard deviation. In all likelihood, all we will know is the sample. Now, what if we could take this sample and we could use it to predict these things? What if we could take a sample and predict mu using x bar and s? Here's the picture. We don't know much in this picture about the population, but we're able to take a sample. If we take a sample, then we can establish the size of that sample, which is n, and we can quickly identify x bar and s. Suppose we take a sample, we know x bar and s. Can we establish a confidence interval for mu? That's the question. Can we use the sample descriptive statistics to infer values of mu? And of course the answer to that is yes. This would be inferential statistics. So the central limit theorem allows us to use x bar and s to establish a confidence interval for mu. The idea is that if the x bars of infinite numbers of samples are scattered around mu, then if you take an x bar, then mu will be close to x bar with the same relationship. Now let's take a given sample. Given x bar and s, we can establish a confidence interval for mu, the population mean. And that mu for the population mean would have a lower bounds and an upper bounds. In other words, we might be 95% certain that mu lies between the lower bounds and the upper bounds. We might be 90% confident. We might be 99% confident. All that it matters there is that we establish the boundaries and we set the confidence levels and use our z-scores appropriately. Now, I want to thank you very much for your support. I know this is not real exciting information, but it will get there. Just be patient and bear with me. We're going to arrive. As always, may the odds be ever in your favor. unless you and I are in the same competition. Then it's every man for himself. You have a good day.